Subscribe to the channel so you don't miss out on any of these videos. Space is a vast tapestry, filled with cosmic phenomena that defy human understanding and challenge the boundaries of our knowledge. Among these marvels, one of the most captivating mysteries lies in the remnants of stars that have outlived their prime, the enigmatic white dwarfs. These compact stellar corpses, once low-mass stars, offer a profound glimpse into the fate of stars similar to our own Sunday. By tracing the life cycle of low-mass stars, we uncover clues not only about their final stages but also about the age of the galaxy itself. These faint, cooling stars are like cosmic timekeepers, silently marking the eons. Through this journey, we will dive deep into the story of white dwarfs, exploring their formation, the unique processes that shape their structure, and the invaluable information they reveal about the universe's history. Low-mass stars, such as those with masses less than about 8 times that of the Sun, begin life much like their more massive counterparts. Formed within dense clouds of gas and dust, these stars emerge from gravitational collapse, igniting nuclear fusion in their cores as they achieve the necessary temperature and pressure. For a star like our Sun, this fusion process primarily involves converting hydrogen into helium through a series of reactions, which releases energy and enables the star to achieve stability. This equilibrium, a delicate balance between the inward force of gravity and the outward pressure generated by nuclear fusion, characterizes what we know as the main sequence phase, where a star spends the majority of its life. As a low-mass star ages, it eventually exhausts the hydrogen fuel in its core. With no hydrogen left to fuse, the core contracts under gravity, and temperatures rise, initiating the fusion of hydrogen in a shell surrounding the core. This process causes the star's outer layers to expand dramatically, turning it into a red giant. In this phase, the star's size can increase up to several hundred times its original diameter, although it grows cooler on the surface, acquiring the characteristic reddish hue of giant stars. This red giant phase is relatively brief compared to the star's main sequence lifespan, lasting only a few million years. In the red giant phase, the core of the star continues to contract and heat up until it reaches a temperature sufficient to ignite helium fusion, if the star has enough mass. This phase, known as the helium flash, sees helium nuclei fuse to form carbon and oxygen in a process called the triple alpha reaction. However, once the helium in the core is exhausted, fusion ceases again, and the core undergoes further contraction. For low-mass stars like the Sun, there is not enough gravitational pressure to sustain further fusion into heavier elements beyond carbon and oxygen. Consequently, the star cannot resist gravitational collapse indefinitely, and ultimately sheds its outer layers into space, creating a planetary nebula, a dazzling, colorful shell of ionized gas that represents the star's outer layers drifting away. What remains is the core, a dense, compact object that lacks the energy to initiate further nuclear reactions. This remnant is the white dwarf. Despite its small size, typically no larger than Earth, a white dwarf possesses a mass comparable to that of the Sun. This extraordinary density results from the unique properties of matter under extreme compression, known as degenerate matter. Unlike in the cores of main sequence stars, where atoms maintain distinct nuclei surrounded by electron clouds, the atoms in a white dwarf are packed so closely that the electrons are forced into close proximity, creating electron degeneracy pressure. This quantum mechanical effect prevents further collapse by counteracting gravity and gives white dwarfs their structural stability. As white dwarfs age, they begin a long and slow cooling process. Having no fuel left to burn, they can no longer generate energy through fusion. Instead, they gradually radiate away their residual heat over billions of years, growing dimmer and cooler with time. During this cooling phase, the temperature of a white dwarf decreases progressively, but given its intense initial heat, this process takes an immense span of time. Some white dwarfs observed today have been cooling for almost the entire age of the universe, making them some of the oldest objects in the galaxy. In studying white dwarfs, astronomers have found that their cooling rates provide a natural clock for estimating the age of the galaxy. By examining clusters of stars that contain white dwarfs, scientists can approximate the time these stars began cooling. As white dwarfs cool in a predictable manner, their temperatures serve as markers of time, allowing researchers to infer how long it has been since these stars entered their final stage. This technique, known as white dwarf cosmochronology, has provided evidence that the oldest white dwarfs in the Milky Way have been cooling for approximately 12 to 13 billion years, aligning closely with estimates of the galaxy's age. One of the fascinating aspects of white dwarfs is their potential to evolve into even stranger objects over unimaginable timescales. As a white dwarf cools, it can crystallize, a process in which atoms lock into a fixed lattice structure as the thermal energy diminishes. Astronomers have observed evidence of crystallization in some white dwarfs, noting slight slowdowns in their cooling rates as they approach this phase. In essence, the white dwarf's core solidifies, turning it into an enormous crystal of oxygen and carbon. This crystallization adds a poetic twist to the life story of these stars. After blazing as giants, they end as cold, dark diamonds scattered across the cosmos. In rare cases, white dwarfs can undergo an explosive resurgence. If a white dwarf resides in a binary system with a companion star, it may siphon gas from its neighbor. As this material accumulates on the white dwarf's surface, it can eventually ignite in a runaway thermonuclear reaction, resulting in a dramatic nova or even a Type I supernova. These supernovae are particularly significant because they shine with a known luminosity, allowing astronomers to measure distances across vast regions of space. Through this process, white dwarfs contribute not only to the enrichment of the interstellar medium with heavy elements, but also to our ability to map the universe's structure and expansion. White dwarfs hold clues not only about the lives of stars but also about the chemical evolution of galaxies. When low-mass stars reach the end of their lives, they release carbon, nitrogen, and other heavier elements into space, enriching the interstellar medium and fueling the formation of future generations of stars and planets. Without this continual cycle of birth, death, and rebirth, the complex chemistry necessary for planetary systems, and potentially life itself, would not exist. White dwarfs, therefore, represent a critical link in the cosmic chain of existence, a bridge between generations of stars that facilitates the ongoing development of the galaxy. Moreover, white dwarfs raise profound questions about the ultimate fate of the universe. Given enough time, all stars, regardless of their initial mass, will eventually reach an endpoint as remnants, white dwarfs, neutron stars, or black holes. Over trillions of years, as star formation declines and galaxies exhaust their gas reserves, the universe will enter an era dominated by remnants. White dwarfs, which can persist for billions or even trillions of years, are anticipated to be among the last remaining luminous objects. In a universe heading towards a state of entropy, these quiet stellar embers will continue to glow faintly as they gradually fade into obscurity, marking the twilight of cosmic history. What we have uncovered through the study of white dwarfs speaks volumes about our place in the cosmos. Every white dwarf is a testament to the power of nuclear fusion, the influence of quantum mechanics, and the inexorable passage of time. These ancient stellar relics serve as cosmic archaeologists, preserving the record of the galaxy's history, from its earliest formations to its present state. In observing these stars, we are not only looking at the remains of distant suns but also gaining insights into the grand mechanisms that shape galaxies, distribute elements, and ultimately, make life possible. As we delve deeper into the mysterious nature of white dwarfs, we find that their study reveals both the resilience and fragility of stars. The extreme density and temperature within these stellar remnants make them unique laboratories for studying the behavior of matter under conditions that cannot be replicated on Earth. Inside a white dwarf, the intense gravitational force compacts matter so tightly that atomic nuclei are squeezed close together, and electrons are forced to occupy higher energy states due to the Pauli exclusion principle. This quantum effect, known as electron degeneracy, is a crucial force that prevents the white dwarf from collapsing under its own gravity. Without electron degeneracy, these remnants of once bright stars would continue collapsing until they reached a far more exotic state, perhaps even a neutron star or black hole. The physical principles that stabilize white dwarfs help us understand the limits of stellar evolution and illuminate the strange realm of quantum mechanics at astronomical scales. One intriguing aspect of white dwarfs is their relatively stable nature, allowing them to persist in their cooling phase for billions of years. Theoretical models suggest that after tens of billions of years, a white dwarf will eventually cool to the point where it no longer emits any significant heat or light, becoming a black dwarf. However, due to the immense timescales involved, longer than the current age of the universe, no black dwarfs are expected to exist yet. This hypothetical final stage represents a future we have yet to witness, a quiet end where these stellar remnants fade entirely into darkness, leaving behind only their gravitational presence. The cooling process of white dwarfs has become a powerful tool for astronomers to date various structures in the galaxy. Since white dwarfs cool at predictable rates, they act as stellar clocks, enabling scientists to estimate the ages of star clusters and even portions of the galaxy. By observing a population of white dwarfs within a cluster, astronomers can determine the age of the cluster based on how long it has taken the coolest and faintest white dwarfs to reach their current temperature. This technique, known as white dwarf cooling age dating, has provided age estimates for some of the oldest star clusters in the Milky Way, offering insights into the timeline of galaxy formation and the age of the universe itself. The process of white dwarf cooling, though seemingly simple, involves several complex stages. When a star first becomes a white dwarf, it is incredibly hot, often with surface temperatures exceeding 100,000 Kelvin. In this early phase, known as the young white dwarf stage, the star shines brightly in the ultraviolet spectrum. Over time, however, it begins to lose its residual thermal energy, cooling at a relatively rapid rate. The cooling rate gradually decreases as the white dwarf's temperature drops, leading to an extremely slow decline in brightness over billions of years. This cooling is affected by factors such as crystallization within the white dwarf's core, a phenomenon discovered relatively recently. As the white dwarf cools, its atoms, primarily carbon and oxygen, begin to lock into a crystalline structure, similar to how water freezes into ice. This process releases latent heat, temporarily slowing the cooling rate and creating a plateau phase where the temperature and luminosity change very slowly. This crystallization process was observed in a large population of white dwarfs by astronomers using data from the Gaia Space Observatory, which confirmed that older white dwarfs cool at a slower rate than previously anticipated due to this unique phase transition. This discovery not only altered our understanding of white dwarf evolution but also provided new tools for fine-tuning the age dating of stellar populations. The role of white dwarfs in the cosmos extends beyond their contribution to our understanding of stellar aging. They also play a critical part in enriching the interstellar medium. During the red giant phase, stars lose a significant portion of their mass through stellar winds, expelling elements like carbon, nitrogen, and oxygen into space. These elements are crucial for the formation of new stars and planets, as well as for the development of complex molecules necessary for life. By dispersing these elements into the cosmos, low-mass stars effectively seed the galaxy with the building blocks of future generations of stars, planets, and potentially even life. This cycle of enrichment underscores the interconnected nature of stellar evolution and the continuous recycling of matter within galaxies. Furthermore, white dwarfs are intimately linked to one of the most powerful tools in observational cosmology, Type Ia supernovae. When a white dwarf is part of a binary system with a companion star, it may draw material from its partner, accumulating mass on its surface. If the white dwarf's mass approaches the Chandrasekhar limit, approximately 1.4 times the mass of the Sun, it can no longer be supported by electron degeneracy pressure and undergoes a catastrophic collapse, triggering a thermonuclear explosion. This explosion results in a Type Ia supernova, a violent event that completely disrupts the white dwarf and releases an immense amount of energy. Type Ia supernovae are particularly valuable to astronomers because they have a consistent peak luminosity, which makes them excellent standard candles for measuring cosmic distances. By comparing the observed brightness of these supernovae to their intrinsic brightness, scientists can calculate their distances from Earth. This property has been crucial for mapping the expansion of the universe and provided key evidence for the existence of dark energy, an unknown force driving the accelerated expansion of the cosmos. Thus, white dwarfs indirectly help us probe one of the deepest mysteries of modern cosmology. White dwarfs are also intriguing in the context of future galactic evolution. As stars deplete their nuclear fuel, the galaxy will gradually shift from a place of active star formation to one filled with stellar remnants. In this distant future, white dwarfs, along with neutron stars and black holes, will become the primary inhabitants of the galaxy. Over unimaginably long timescales, the Milky Way will evolve into a collection of ancient stellar corpses, remnants of the stars that once fueled its dynamic cycles of birth and death. This phase, often referred to as the degenerate era, represents a future epoch in which the universe will be dominated by cooling white dwarfs, silently drifting through the remnants of their once vibrant stellar neighborhoods. In addition to being stellar relics, white dwarfs may also hold the key to understanding the ultimate fate of the universe. One scenario for the far future of the cosmos is known as the Big Freeze, or heat death, where all energy becomes evenly distributed, and temperature differences vanish. In this bleak vision, white dwarfs would be among the last glowing objects in the universe. As they gradually cool to near absolute zero, they would finally reach the end of their journey, becoming cold, dark remnants scattered across an unimaginably vast and empty cosmos. The final glow of these stars would mark the last vestiges of visible light in a universe fading into eternal darkness. Interestingly, recent research into white dwarfs has uncovered new insights into their magnetic properties. Some white dwarfs possess extraordinarily strong magnetic fields, with strengths up to 1,000,000 times greater than Earth's. These magnetic fields may arise from the star's rotational history, or from complex interactions within its dense core. Magnetic white dwarfs offer a fascinating glimpse into the extremes of magnetic phenomena, and studying them helps astronomers understand the diversity of end-stage stellar remnants. These magnetic properties could also impact the cooling rates and structural stability of white dwarfs, adding another layer of complexity to the physics of these ancient objects. In their silent, enduring glow, white dwarfs hold an almost poetic symbolism. They represent a quiet culmination, a gradual relinquishment of energy and light, and ultimately, a reminder of the transitory nature of all stellar life. From blazing giants to quiet, crystalline remnants, white dwarfs embody the full circle of a star's journey, offering a cosmic perspective on life and death that stretches far beyond human timescales. Studying these remnants allows us to confront profound questions about existence and continuity, about the birth and eventual death of all things. White dwarfs remind us that, like the stars themselves, everything in the universe is part of a vast, interconnected cycle, where even the remnants of the past become the seeds of the future. The enduring presence of white dwarfs in the cosmos speaks to the incredible durability of these stars' remnants, as well as their significance as silent custodians of the universe's history. They are like ancient archives, holding within them the records of galactic evolution, star formation, and elemental synthesis that stretch back billions of years. Each white dwarf in the galaxy is a chapter in the larger story of our cosmos, encapsulating in its core the story of a star's entire life. From formation, through its main sequence, to its death as a faint ember of what it once was. And because they cool so slowly, they offer astronomers a direct line to studying the ancient history of the Milky Way, giving us a way to glimpse the distant past. White dwarfs also serve as an intriguing comparison point when it comes to different types of stellar remnants. Unlike neutron stars or black holes, which are the byproducts of more massive stars, white dwarfs are unique in that they arise from the more common, lower-mass stars. This difference makes them far more numerous in the universe, as stars similar in mass to our Sun are abundant and long-lived. Neutron stars and black holes, while fascinating in their own right, result from stars with far shorter lifespans, leaving white dwarfs as the most enduring and prevalent relics of the stellar population. It is estimated that in our own galaxy alone, there may be as many as 10 billion white dwarfs, each contributing to the vast stellar graveyard that surrounds us. As cosmic time moves forward, white dwarfs will continue to influence the galaxies they inhabit in ways we are only beginning to understand. With each passing eon, as galaxies evolve and interact, the role of these stellar remnants becomes more central. In the far future, when star formation has mostly ceased and only these ancient remnants remain, white dwarfs will stand as the quiet keepers of the galaxy's story, lingering long after the last new stars have been born. The Milky Way itself, shaped by countless generations of stars, will ultimately become a landscape dominated by these faint and ghostly remnants. In recent years, technological advances have allowed scientists to study white dwarfs with unprecedented detail. Instruments like the Hubble Space Telescope, the Gaia mission, and various ground-based observatories have provided high-resolution images and spectra of white dwarfs across different environments, from isolated stars to those embedded in dense star clusters. Observing white dwarfs in different settings gives scientists clues about how environmental factors, such as proximity to other stars or the density of the surrounding medium, can affect their cooling and behavior over time. Gaia's comprehensive survey of stars in our galaxy, in particular, has given astronomers a unique window into the life cycles of countless stars, enabling them to track the ages and properties of white dwarfs in ways that were previously impossible. One of the most intriguing discoveries about white dwarfs is the phenomenon of pulsating white dwarfs, known as DAV, DBV, or ZZ Ceti stars, depending on their composition and temperature. These stars exhibit periodic changes in brightness as waves of pulsations ripple through their interiors. By studying these pulsations, much like how seismologists study earthquakes to probe the Earth's interior, astronomers can gain insights into the inner structure of white dwarfs. This field, known as astroseismology, has proven to be a valuable tool for understanding the composition and evolution of these stellar remnants. Through these pulsations, scientists can directly measure properties like the thickness of the outer hydrogen or helium layers, providing a window into the final stages of stellar evolution. White dwarfs may even be implicated in the mysterious phenomenon of fast radio bursts, FRBs, highly energetic, millisecond-long bursts of radio waves that originate from distant galaxies. While the exact source of FRBs remains unknown, some researchers have speculated that they could be linked to certain types of white dwarfs or even interactions involving magnetic white dwarfs and neutron stars. If white dwarfs are indeed connected to FRBs, it would mark yet another example of how these quiet stellar remnants can produce profound cosmic phenomena, bridging the gap between the serene final stages of stellar evolution and some of the universe's most energetic outbursts. The diversity and range of phenomena associated with white dwarfs continue to expand, challenging and refining our understanding of these stellar remnants. Their influence stretches across a range of astrophysical fields, from galactic archaeology to high-energy astrophysics, as they reveal more about not only their own nature but also the workings of the universe at large. These compact stars, long considered quiet and inert, are proving to be complex objects with surprising potential to impact their surroundings and reveal fundamental truths about the cosmos. White dwarfs also provide a natural testing ground for theories of dark matter. Certain types of white dwarfs exhibit unusual cooling rates or variations in brightness that some researchers speculate could be due to interactions with hypothetical dark matter particles. As dark matter is thought to make up a significant portion of the universe's mass but remains largely invisible and undetectable, white dwarfs could play a pivotal role in advancing our understanding of this elusive component. If interactions between white dwarfs and dark matter are confirmed, it could be a revolutionary breakthrough in physics, providing the first direct evidence of dark matter's presence and its impact on observable phenomena. Beyond their scientific significance, white dwarfs offer a kind of cosmic mirror for humanity. They remind us of the cycles that govern not only stellar evolution but life itself, with each stage of existence contributing to a larger, interconnected whole. The atoms in our bodies, forged in the hearts of ancient stars, eventually find their way back into the galaxy's endless cycle of birth, death, and rebirth. White dwarfs encapsulate the culmination of this journey, a point of stasis at the end of a star's life where it no longer burns with the fire of youth but instead glows quietly, a lasting reminder of its former brilliance. In contemplating the life and eventual quiet cooling of white dwarfs, we are, in a way, looking into the long-term fate of our own sun and solar system. In roughly 5 billion years, our sun will swell into a red giant, shed its outer layers, and leave behind a white dwarf, a stellar cinder that will illuminate the distant future with a faint, fading glow. That remnant will be the final chapter of our sun's story, a testament to the transient yet impactful journey of a star that has sustained life on Earth for billions of years. The study of white dwarfs is, ultimately, a study of endurance, of persistence in a universe that is ever-changing and impermanent. These stellar remnants endure long after their flames have extinguished, offering a quiet but potent testimony to the life cycles that shape our cosmos. White dwarfs may seem unremarkable at first glance, small, dim points of light scattered across the night sky, but they hold secrets that stretch back to the dawn of the universe and reach forward into its distant future. In the grand tapestry of the universe, white dwarfs are a constant presence, a reminder of what once was and a glimpse of what is yet to come. These stellar remnants, suspended in time, continue to guide our understanding of the galaxy's history, the evolution of matter, and the fate that awaits all stars. As we study these ancient embers, we gain not only scientific knowledge but also a profound appreciation for the vast, interconnected processes that have shaped the universe and, by extension, our very existence. The fascinating story of white dwarfs and their significance in the universe continues to unfold as scientists make new discoveries and refine existing theories. At the heart of this ongoing exploration is the question of what white dwarfs reveal about the limits of stellar endurance and the ultimate fate of matter itself. As the universe ages, white dwarfs, with their extraordinary longevity, offer us a glimpse into how the cosmos might look in eons to come, long after new star formation has ceased. One of the most captivating aspects of white dwarfs is their role as time capsules for the galaxy. As remnants of stars that once blazed brightly, white dwarfs contain elements and structures that were formed during the main sequence phase of their parent stars' lives. This means they carry within them traces of early galactic history, including the original abundances of various elements that were present when the Milky Way was young. By studying these fossilized stars, scientists gain insight into the chemical evolution of the galaxy and the processes that led to the formation of planets and life as we know it. The oldest white dwarfs serve as a kind of cosmic chronometer, allowing astronomers to estimate the age of the oldest stellar populations. Since white dwarfs cool at predictable rates, their temperatures can provide an approximate timeline of when the star first evolved into a white dwarf. This cooling age can then be used to infer the approximate time of formation for ancient star clusters and even the galaxy itself. Through this process, white dwarfs contribute to our understanding of not only stellar evolution, but also the timeline of cosmic events, including the formation of the Milky Way and the early stages of star formation. The very cooling process of white dwarfs is a remarkable phenomenon, involving intricate physics that challenges and extends our understanding of matter at extreme densities. As a white dwarf cools, its luminosity gradually decreases, and it undergoes a transformation that is almost unimaginably slow. At the outset, a newly formed white dwarf may shine with a significant degree of brightness, especially if it's the remnant of a massive star. However, as it ages, it loses energy, not by fusion, but through the gradual release of residual heat. Unlike main sequence stars, which shine due to nuclear reactions, white dwarfs glow solely because of this stored thermal energy, slowly radiating away their warmth. What makes this cooling process even more fascinating is that it is governed by quantum mechanical principles, particularly the concept of electron degeneracy pressure. In a white dwarf, atoms are packed so closely that electrons are forced into higher energy states, preventing the star from collapsing further under gravity. This pressure is not temperature dependent, which is why white dwarfs do not reignite fusion even as they cool. Instead, they transition to lower energy levels without undergoing significant structural changes, allowing them to exist in a relatively stable state for billions, even trillions, of years. As white dwarfs cool, they eventually approach a theoretical state known as a black dwarf. This would be an object that has cooled so extensively that it no longer emits detectable light, becoming essentially an invisible remnant of what was once a star. However, given the age of the universe, it is unlikely that any black dwarfs currently exist. The cooling process for a white dwarf to reach such a state would take so long, trillions of years, that it far exceeds the universe's current age. This makes the idea of black dwarfs largely hypothetical, but it does provide a glimpse into the ultimate end state of matter in a universe governed by entropy, where all energy eventually dissipates. The implications of white dwarfs extend beyond their own evolution to affect the entire fabric of galactic dynamics. As these stellar remnants persist, they gradually populate the galaxy's halo and disk, forming what is essentially a cosmic graveyard of stellar material. Over time, as white dwarfs increase in number and darken, they contribute to the overall mass and gravitational influence of the galaxy. Though small in size and faint in luminosity, the sheer number of white dwarfs in the Milky Way alone suggests that they have a collective gravitational effect that cannot be ignored. This accumulation of dark, dense remnants may even influence the motions of stars and contribute to the stability of galactic structures over the long term. In addition to their role as remnants, white dwarfs are known to participate in complex binary interactions, which can lead to some of the universe's most energetic and dramatic events. When a white dwarf is part of a close binary system, it can occasionally siphon material from its companion star. This material buildup can trigger intense reactions on the white dwarf's surface, leading to phenomena such as novae, where the star experiences a sudden and intense brightening. In extreme cases, if a white dwarf accumulates enough mass to reach a critical threshold known as the Chandrasekhar limit, about 1.4 times the mass of the Sun, it can undergo a Type I supernova, a powerful explosion that completely obliterates the white dwarf. Type I supernovae are particularly significant in astronomy because they serve as standard candles for measuring cosmic distances. The consistency in the peak luminosity of these explosions allows astronomers to calculate distances to far-off galaxies, providing essential data for mapping the structure of the universe and understanding its expansion rate. In fact, the discovery of the accelerating expansion of the universe, a finding that earned a Nobel Prize in physics, was made possible through observations of Type I supernovae. These explosions, rooted in the quiet, enduring presence of white dwarfs, have reshaped our understanding of cosmology and continue to influence the study of dark energy and the ultimate fate of the universe. The study of white dwarfs has even extended into the realm of planetary science, revealing unexpected discoveries about planetary systems around these stellar remnants. Observations have shown that some white dwarfs host debris disks, likely remnants of planetary systems that once orbited the progenitor star. Occasionally, scientists detect the spectral fingerprints of heavy elements, such as calcium or magnesium, in the atmospheres of white dwarfs. Since these elements should sink rapidly into the star's interior, their presence suggests that these white dwarfs are actively accreting material from orbiting debris, possibly from shattered planets or asteroids that once orbited the original star. The discovery of this pollution in white dwarf atmospheres is groundbreaking because it offers indirect evidence of planetary systems that survived the cataclysmic changes in their host stars. It suggests that planets may endure the transition of their parent stars into white dwarfs, albeit in fragmented or disrupted forms. This finding has implications for our understanding of planetary system evolution, as well as the potential longevity of planets in general. In our own solar system, this raises intriguing questions about what might happen to the outer planets, such as Jupiter and Saturn, when the Sun eventually becomes a white dwarf. While inner planets like Earth will likely be engulfed during the red giant phase, the gas giants could potentially remain in orbit around the Sun's white dwarf remnant, offering a distant parallel to these observed systems. In the distant future, as our galaxy continues to evolve, white dwarfs will remain as some of the longest-lasting celestial objects. They will outlive the youngest stars currently forming in the galaxy, persisting long after main sequence stars have burned through their fuel. The Milky Way, eventually merging with the Andromeda Galaxy in a few billion years, will host an even more diverse stellar population, including countless white dwarfs from both galaxies. These remnants will become part of a new galactic structure, perhaps forming a vast, diffuse field of faint, aging stars that emit only the faintest glimmers of light. As the Milky Way merges with Andromeda and eventually forms a new, massive elliptical galaxy, white dwarfs will serve as a stable and enduring presence amidst the cosmic reshuffling. The collision itself, expected to be relatively gentle on the scale of galactic mergers, won't obliterate most stars but will dramatically alter their orbits and the galactic structure. In this chaotic reorganization, white dwarfs will drift in the newly formed galaxy's core, halo, and vast outer regions, slowly cooling as they enter into a state of extreme age and isolation. In this distant cosmic future, white dwarfs may even interact with new generations of stars formed during the merger. These interactions, though rare, could lead to gravitational encounters that change the trajectories of stars, or, in some cases, cause the accretion of material onto a white dwarf from passing interstellar matter or nearby stars. While these interactions may be sporadic, they underscore how white dwarfs can play a subtle but persistent role in galactic dynamics, affecting not just their immediate stellar neighbors but the broader distribution of mass and gravitational forces across the galaxy. The eventual fate of white dwarfs lies in their ability to endure in ways few other celestial objects can. Unlike neutron stars and black holes, which are formed from much more massive progenitors and are generally less common, white dwarfs are numerous and are dispersed widely throughout galaxies. This abundance makes them central to understanding the long-term evolution of the universe. In the far reaches of time, after all sources of new energy production have ceased, white dwarfs will continue to cool until they reach a state of near-total darkness. Their energy will be nearly exhausted, their luminosity reduced to the faintest glimmer or extinguished entirely in the form of hypothetical black dwarfs. Though black dwarfs are purely theoretical at this stage, as none are expected to exist yet due to the universe's relatively young age, the concept provides a glimpse into the universe's distant endgame. Black dwarfs represent the final evolutionary stage of stellar remnants, marking the ultimate dissipation of energy into the cosmic void. The transition of a white dwarf into a black dwarf is expected to be staggeringly slow, potentially taking hundreds of trillions of years. The existence of black dwarfs, should they ever come to be, would be evidence of a universe in which all stars have burned out, leaving only the faint glow of cooling remnants and dark matter. This era, sometimes referred to as the degenerate era, in cosmology, envisions a universe dominated by stellar remnants, white dwarfs, neutron stars, and black holes, with all other sources of light extinguished. White dwarfs would be among the final vestiges of the stars that once populated the cosmos. The fate of these remnants, existing in a state of permanent darkness, with even their residual heat dissipated, depicts a universe where entropy has reached its apex, and all processes that once sustained life and structure have ceased. This profound future for white dwarfs not only challenges our understanding of stellar physics, but also reshapes our perceptions of time and existence. The longevity of white dwarfs underscores the universe's immense scale, where even billions of years are only a brief chapter in the cosmic narrative. As scientists study these remnants, they gain insight not only into the life cycle of stars but also into the ultimate fate of matter, energy, and structure in a universe governed by the laws of thermodynamics. White dwarfs also offer a sobering perspective on the fragility of stellar life and the temporary nature of luminosity itself. All stars, regardless of their mass or brilliance, are ultimately fated to an endpoint where they can no longer sustain fusion. Low-mass stars, which once burned efficiently and quietly over billions of years, undergo this transition into white dwarfs as a testament to both endurance and finality. In the vast timeline of the universe, the seemingly eternal brilliance of stars is, in reality, fleeting, and white dwarfs embody this transition between life and entropy. These stellar remnants also help bridge our understanding of the early universe with the cosmic future. By analyzing the properties of white dwarfs, particularly their cooling rates, scientists gain crucial data about the age of various stellar populations. White dwarfs found in ancient star clusters, such as globular clusters, allow researchers to date these clusters, often revealing them to be nearly as old as the universe itself. This provides a window into the conditions that existed not long after the Big Bang, when the first stars and galaxies formed. The discovery and study of white dwarfs have also spurred advances in theoretical physics, particularly in areas that test our knowledge of quantum mechanics and thermodynamics. The idea of electron degeneracy pressure, which prevents a white dwarf from collapsing, showcases the quantum mechanical principles that govern matter at the smallest scales. Degeneracy pressure is a phenomenon unique to extremely dense objects like white dwarfs, where the rules of classical physics give way to quantum effects that stabilize the star against gravitational collapse. These principles, first conceptualized in the early 20th century, continue to be explored and refined as scientists uncover new layers of complexity within stellar remnants. In understanding white dwarfs, we also gain insight into the limitations of matter under extreme conditions. With temperatures reaching millions of degrees shortly after their formation, white dwarfs gradually cool as they radiate their stored heat into space. This cooling process is extraordinarily slow, making white dwarfs some of the most enduring objects in the universe. As they age, their outer layers may crystallize, transitioning from a gaseous state to a solid structure over billions of years. This crystallization process, which has been observed in a few nearby white dwarfs, is akin to the formation of a giant cosmic diamond, revealing yet another layer of beauty in these stellar relics. Ultimately, white dwarfs represent both the end of a stellar journey and the beginning of a new chapter in the life of the galaxy. Their existence poses profound questions about the nature of time, the endurance of matter, and the ultimate fate of the universe. As scientists continue to observe and study these fascinating remnants, they unlock more mysteries about the cosmos, bringing us closer to understanding the processes that govern both the creation and eventual decay of all things. The story of white dwarfs is a reminder of the intricate and interconnected nature of the universe, where even the smallest details hold keys to the most profound truths. From the early life stages of a low-mass star to the quiet, enduring glow of a white dwarf, these remnants tell a story of resilience, transformation, and cosmic memory. As we look to the future of astronomy, the study of white dwarfs will no doubt remain at the forefront, guiding us toward a deeper understanding of our galaxy, our universe, and our place within it. White dwarfs, in many ways, serve as cosmic timekeepers. Their incredibly slow cooling rates provide a measurable timeline that can be used to gauge the ages of star clusters and even sections of the galaxy itself. By understanding the cooling rate and temperature of white dwarfs, scientists can estimate how long they have been radiating heat and thus approximate when their progenitor stars first formed. This technique has been invaluable in determining the ages of some of the oldest known stellar populations, such as the stars and globular clusters. These ancient clusters, which orbit the Milky Way's halo, contain a substantial number of white dwarfs, suggesting they formed in the early epochs of the universe. In a broader sense, studying white dwarfs offers clues to the overall history and evolution of the Milky Way. By examining the distribution and ages of white dwarfs across different parts of the galaxy, scientists can reconstruct the formation history of the galactic disk, bulge, and halo. White dwarfs found in the galactic disk, for example, are often younger than those in the halo, indicating that the disk formed later. This distribution tells a layered story of star formation, migration, and eventual cooling across billions of years. Essentially, white dwarfs act as a historical record, one that allows us to read back into the galaxy's past and piece together its formation. This methodology has profound implications for cosmology. Since white dwarfs provide a consistent way to estimate stellar ages, they help calibrate other astronomical age-dating techniques, lending accuracy to our models of the universe's expansion and history. The age estimates derived from white dwarfs have even supported and verified other age calculations made through measurements of the cosmic microwave background and the ages of the oldest stars. As these diverse approaches converge, they lend greater confidence to our understanding of the universe's overall timeline, from the Big Bang to the present. White dwarfs also offer unique insights into the potential existence of dark matter, one of the most mysterious components of the cosmos. Because white dwarfs are so stable and long-lasting, they have the potential to interact subtly with dark matter in ways that could provide indirect evidence of its presence. Scientists speculate that dark matter particles might occasionally interact with the dense material within a white dwarf, altering its temperature or composition in subtle ways. Some research even suggests that if dark matter particles collide with atoms inside white dwarfs, they could theoretically produce observable effects, like unexpected heating. While this is still speculative, it highlights how white dwarfs might act as silent witnesses to the hidden mass of the universe. Furthermore, white dwarfs have inspired research into the possibility of life in regions of space that we once thought inhospitable. Though white dwarfs are no longer capable of supporting fusion and have low luminosity, some astronomers have speculated that exoplanets could orbit these faint stars within a habitable zone, where temperatures might allow for liquid water. If such planets were to exist and have retained their atmospheres, it opens up the intriguing question of whether life might adapt to orbiting a star that no longer shines with the full force of fusion energy. Discovering exoplanets around white dwarfs could challenge our understanding of habitability, suggesting that life could survive in much more diverse environments than previously believed. White dwarfs have also inspired astronomers to consider alternative forms of energy generation on an unimaginable timescale. Some theoretical physicists propose that as stars approach the end of their fusion lifespans, civilizations in the distant future might harness the residual heat and faint light emitted by cooling white dwarfs. While it's speculative, it poses fascinating possibilities for a far future universe where advanced civilizations utilize the last vestiges of stellar energy to sustain themselves. This concept, sometimes described as a Dyson sphere around a white dwarf, highlights how even dying stars might serve as valuable resources in a universe nearing heat death. On the other end of the spectrum, white dwarfs provide a setting for some of the most extreme and catastrophic phenomena in astrophysics. Type Ia supernovae. When a white dwarf accumulates enough mass, often through accretion from a companion star, it can ignite in a runaway fusion reaction, exploding with a brilliance that outshines entire galaxies. These Type Ia supernovae are of particular interest to astronomers because they serve as standard candles, providing a reliable measure of distance across vast cosmic scales. By analyzing these explosions, scientists have been able to make groundbreaking discoveries about the expansion rate of the universe, even uncovering the acceleration driven by dark energy. This connection between white dwarfs and cosmic explosions underscores the dual nature of these remnants. While they are peaceful, stable objects under normal conditions, they have the potential to be some of the most violent and transformative forces in the cosmos under specific circumstances. The idea that such calm, slowly cooling stars can become agents of cosmic upheaval adds a layer of mystery and grandeur to their story. It serves as a reminder of the universe's unpredictable and awe-inspiring nature, where objects can transition between phases of quiet endurance and explosive transformation. Interestingly, the formation and evolution of white dwarfs also speak to the fundamental properties of matter under extreme conditions. In a white dwarf, the atoms are so densely packed that they are on the edge of collapsing into a neutron star, and only the pressure from electrons, quantum degeneracy pressure, prevents this fate. This balance between gravity and quantum forces serves as a laboratory for exploring the limits of physics, and understanding white dwarfs has contributed significantly to the fields of quantum mechanics and thermodynamics. In this way, white dwarfs hold a unique place in the universe. They are remnants of a past that reaches back to the early days of star formation, witnesses to the galactic history, and possibly even players in the distant future of the cosmos. They embody the life cycle of stars, the mysteries of matter, and the inexorable progress of time. In a universe where so much is fleeting, white dwarfs offer a rare sense of continuity, serving as silent, resilient markers in the cosmic landscape. These stars also remind us of the vast timescales and forces that shape the cosmos, challenging our perception of time and endurance. Where humanity's history spans a few thousand years, the cooling process of a single white dwarf stretches over billions, emphasizing the unimaginable longevity of these stellar remnants. Their slow cooling not only allows us to peer into the past but also gives us a glimpse of a universe that will continue to evolve long after our brief moment has passed. In a way, white dwarfs stand as symbols of resilience. They endure when their parent stars have exhausted every avenue of energy production, transforming from luminous giants to quiet, cooling remnants. Yet even in their quietude, they hold immense knowledge about the galaxy, the history of star formation, and the limits of physical laws. Through them, we learn not only about the stars themselves but also about the fate of matter in the grand tapestry of the universe. White dwarfs invite us to ponder the profound questions of existence and permanence. They are reminders of the beauty and transience of stellar life, of a cosmos that is both stable and ever-changing. As we continue to explore the mysteries of these stellar remnants, we move closer to understanding the full scope of cosmic evolution, the fate of stars, and perhaps even the destiny of the universe itself. The profound endurance of white dwarfs not only marks them as cosmic relics but also symbolizes a natural endpoint in the grand life cycle of stars. As low-mass stars reach the conclusion of their active lives, they gradually transition through red giant stages and eventually shed their outer layers. This process creates spectacular planetary nebulae, gaseous shells that float away from the core in often stunning shapes and colors, leaving behind the dense, cooling white dwarf. The formation of planetary nebulae in the final stages of a low-mass star's life is one of the most visually striking phenomena in the cosmos. As a star like our Sun exhausts its hydrogen fuel, it expands into a red giant, with its outer layers becoming loosely bound to the core. Eventually, the star's outer material drifts into space, illuminated by the remaining hot core, creating glowing, intricate patterns of gas and dust. These planetary nebulae are short-lived in astronomical terms, lasting only tens of thousands of years, but they leave an indelible mark in the star's evolutionary path. The nebula eventually dissipates into space, enriching the surrounding interstellar medium with heavier elements that can later be incorporated into new stars and planets. When the nebula dissipates, all that remains of the original star is the compact white dwarf at its center. These white dwarfs, no longer undergoing fusion, enter a phase where they slowly radiate their remaining thermal energy into space. The cooling process is extremely gradual, lasting billions of years, and the star's temperature drops incrementally over time. This cooling is one of the most stable phases of a star's life, as the white dwarf simply fades into a darker, colder state without any dramatic shifts. This slow cooling process, controlled by the release of residual heat from the star's dense core, is predictable and measurable, making white dwarfs excellent indicators for astronomers to estimate stellar and galactic ages. The predictable nature of white dwarf cooling has allowed scientists to develop a concept known as white dwarf chronometry. Since white dwarfs cool over time in a consistent manner, astronomers can use their temperatures as a kind of stellar clock. By observing a population of white dwarfs, particularly in globular clusters or certain galactic regions, scientists can estimate the ages of these groups of stars, and by extension, the age of the galaxy itself. This method has been instrumental in confirming that the oldest white dwarfs are around 13 billion years old, which aligns with current estimates of the age of the Milky Way and the universe. One of the most intriguing aspects of white dwarfs is how they contribute to our understanding of the elements within the universe. Throughout their lives, stars generate heavier elements through fusion, such as carbon, oxygen, and other elements up to iron. When a star enters the white dwarf phase, it carries within it the record of all these nuclear processes. The white dwarf's composition reflects the fusion history of its progenitor star, essentially acting as a stellar archive of nuclear reactions that occurred within its core. This information is invaluable for researchers trying to piece together how different elements formed in the universe and how they were distributed across the cosmos. In some cases, white dwarfs exhibit additional phenomena that provide even more insights. A specific type of white dwarf known as a pulsating white dwarf undergoes rhythmic brightness variations. These pulsations are caused by periodic expansions and contractions in the star's outer layers, driven by temperature changes and specific modes of pressure within the star. By studying the frequencies of these pulsations, astronomers can probe the internal structure of the white dwarf. This method, known as astroseismology, allows scientists to gain a rare glimpse into the star's core composition and density, revealing information about the precise conditions under which various elements fused. Beyond their own life cycle, white dwarfs also interact with their surroundings in ways that can produce extraordinary events. In binary star systems, where a white dwarf has a close companion star, the white dwarf can gravitationally draw material from its companion. This accretion process can lead to phenomena known as novae. As the accreted material accumulates on the white dwarf's surface, it can ignite in a thermonuclear explosion, creating a dramatic increase in brightness that can be observed across great distances. These nova outbursts provide further insight into the physics of accretion and the interaction between compact stellar remnants and their environments. In some cases, however, the accumulation of material on a white dwarf reaches a critical mass, typically around 1.4 times the mass of the Sun, a threshold known as the Chandrasekhar limit. When a white dwarf approaches this mass limit, the pressure from electron degeneracy can no longer counteract the gravitational force. This triggers a catastrophic event, leading to a Type I supernova, where the white dwarf is completely destroyed in a massive explosion. These supernovae are among the most luminous events in the universe, briefly outshining entire galaxies, and they serve as crucial tools for measuring cosmic distances. The consistent peak brightness of Type I supernovae allows astronomers to use them as standard candles, to measure distances across the universe, and to map the rate of cosmic expansion. The use of Type I supernovae as standard candles has been pivotal in one of the most groundbreaking discoveries in modern astrophysics, the accelerated expansion of the universe. Observations of distant supernovae revealed that galaxies are receding from each other at an increasing rate, which led to the postulation of dark energy, a mysterious force driving this acceleration. This discovery fundamentally changed our understanding of the universe's fate, suggesting that its expansion will continue indefinitely, potentially leading to a cold, dark end as galaxies drift apart and star formation ceases. Thus, white dwarfs, through their explosive deaths, have provided essential clues about the large-scale structure and ultimate destiny of the universe. The study of white dwarfs has also raised fascinating questions about the future of stellar remnants on exceedingly long timescales. As white dwarfs continue to cool over billions or even trillions of years, they will eventually become so cold that they no longer emit any detectable light. These objects, referred to as black dwarfs, would represent the final evolutionary state of low-mass stars. Although black dwarfs are purely theoretical at this point, as the universe is not yet old enough for any to have formed, they represent a future where all remaining white dwarfs have faded into darkness. In such a far future universe, black dwarfs would be scattered remnants, serving as silent witnesses to a bygone era of starlight. White dwarfs and their ultimate fate as black dwarfs highlight the concept of entropy, the gradual progression toward disorder and energy dissipation in the universe. The eventual cooling of all stars, and the transformation of matter into inert, cold remnants, illustrates the second law of thermodynamics on a cosmic scale. As the universe ages, it will progress toward a state of maximum entropy, where no usable energy remains, a scenario often referred to as the heat death of the universe. White dwarfs, in their slow and steady cooling, offer a glimpse of this distant, inevitable outcome, a universe where all sources of light and energy have long since faded. In this grand context, white dwarfs serve as reminders of the impermanence of stellar life and the unyielding march of time. They embody a phase of quiet endurance, existing in the twilight between active stardom and ultimate extinction. Observing these stars, we gain a sense of the universe's vast timeline, one that stretches beyond human comprehension and unfolds across billions of years. White dwarfs provide an intimate look at this timeline, showing us the phases of stellar evolution and the forces that will shape the cosmos long after humanity is gone. Yet, within this seemingly somber vision lies an incredible wealth of knowledge. By studying white dwarfs, we learn not only about stars but also about the physical laws that govern matter, energy, and the very fabric of the universe. These remnants reveal the limitations of quantum mechanics, the nature of fusion processes, and the ways in which galaxies evolve. Through white dwarfs, we glimpse both the universe's history and its ultimate fate, tracing the pathways of countless stars that have burned brightly and then faded into the night. The silent, enduring nature of white dwarfs also allows astronomers to probe deeper questions about our galaxy's formation and development. Unlike more massive stars that go supernova in mere millions of years, low-mass stars live for billions, meaning they can serve as long-lasting beacons of cosmic history. White dwarfs, in their final phases, help astronomers piece together the history of star formation in the galaxy, as their ages can be correlated with the age of the regions they inhabit. By examining populations of white dwarfs, researchers can infer patterns of star formation, noting when certain regions of the galaxy were most active in birthing stars. This makes white dwarfs indispensable tools for studying the galactic evolution of the Milky Way and beyond. Furthermore, white dwarfs offer insights into the galaxy's structure. In particular, White dwarfs and globular clusters and the galactic halo provide unique opportunities to examine stellar populations outside the main disk of the Milky Way. Globular clusters are some of the oldest structures in the galaxy, housing stars that formed early in the Milky Way's life. By analyzing the properties of white dwarfs within these clusters, scientists gain a clearer view of the chemical composition and conditions in the early universe. Since these ancient stars have evolved into white dwarfs, they retain signatures of the primordial elements and conditions of their formation, revealing what the early galaxy might have looked like. Another fascinating aspect of white dwarfs is their role in the search for planets beyond our solar system, particularly exoplanets that orbit stellar remnants. While traditional planet hunting methods are often ineffective around dead or dying stars, astronomers have detected planets and planetary debris around white dwarfs. These discoveries have opened up an entirely new field of study, post-main sequence planetary systems. In some cases, material from planets or asteroids has been observed accreting onto white dwarfs, creating visible pollution in the star's atmosphere. This material often contains heavy elements, which typically sink in a white dwarf's intense gravity, indicating recent accretion from surrounding debris. This evidence reveals that planets may survive and even interact with their host stars after the stars have died, providing a glimpse into the long-term evolution of planetary systems. These white dwarf planetary systems hint at the remarkable resilience of planets and the complex dynamics that can unfold in stellar graveyards. For instance, astronomers have detected signs of rocky debris disks around some white dwarfs, similar to the asteroid belt in our solar system. These disks suggest that, after a star has transitioned into a white dwarf, the gravitational disruptions from the red giant phase can cause planetary orbits to shift, leading to collisions and fragmentation of rocky bodies. These fragments can then be drawn toward the white dwarf, producing a visible debris disk and contaminating the white dwarf's atmosphere. Such systems offer a unique perspective on the later stages of planetary evolution and provide clues about the ultimate fate of our own solar system billions of years from now. Moreover, the study of these polluted white dwarfs gives insight into the composition of exoplanetary materials. Since these elements accumulate on the surface of the white dwarf, astronomers can analyze the white dwarf's light spectrum to identify the specific elements present. This technique allows scientists to read the chemical signatures of exoplanetary material, even if they cannot observe the planets directly. Such analyses have revealed the presence of elements like calcium, iron, and magnesium, suggesting that rocky, Earth-like planets might be common around other stars. These findings bridge the study of white dwarfs with the growing field of exoplanet science, enhancing our understanding of planet formation and the potential for Earth-like worlds in other star systems. Looking into the far future, white dwarfs will become one of the last sources of visible light in the universe. As the universe ages, star formation will slow and eventually cease as raw materials are depleted. Large stars will go supernova or collapse into black holes, while smaller stars, like red dwarfs, will finally burn out. As all other forms of starlight vanish, white dwarfs will persist as the final luminous objects, slowly cooling and fading over trillions of years. In a sense, they are the quiet survivors of the cosmos, embodying the ultimate endurance of stellar matter in a universe that is gradually growing colder and darker. The study of white dwarfs thus touches on some of the deepest questions about the universe's past, present, and future. From mapping the Milky Way's formation to probing the composition of ancient planetary systems and contemplating the distant fate of starlight itself, white dwarfs are more than just the remnants of once active stars. They are like cosmic fossils, preserving clues about the universe's earliest conditions and projecting hints about its eventual end. Through their enduring glow and steady cooling, white dwarfs whisper stories of the cosmos, stories that, for as long as they shine, will continue to reveal the secrets of our vast, mysterious universe. As we peer even further into the future, white dwarfs lead us into some of the most mind-bending and humbling aspects of cosmic evolution. Imagine a time trillions of years from now, when these stars have finally radiated all their remaining heat, becoming so-called black dwarfs, cold, dark remnants that barely interact with their surroundings. Although none exist yet, as the universe is still far too young, black dwarfs represent the end stage in the life of a white dwarf, a final phase when even their faint glow has faded away. This vision of black dwarfs illustrates a fascinating aspect of the universe's ultimate fate. In an environment where no new stars are forming, no fusion is taking place, and every once bright object has cooled to near absolute zero, the cosmos will reach a state known as heat death, or maximum entropy. In this scenario, all energy has been dispersed evenly across space, meaning that no work or reactions can take place. White dwarfs, in their fading forms, thus serve as symbols of the eventual quieting of the universe, a universe that, having expended all its available energy, enters an eternal, unchanging state. Even more intriguing is the theoretical notion that black dwarfs, given enough time, may become sites of quantum tunneling events that could theoretically cause them to collapse into black holes. This is an extreme and speculative idea, stemming from the understanding that quantum processes, although rare and difficult to observe, can influence matter over extraordinarily long timescales. In this way, some scientists have speculated that black dwarfs could be drawn into a form of quantum collapse, though such an event would require a span of time so vast that it dwarfs the current age of the universe by unimaginable orders of magnitude. When we look at white dwarfs from this perspective, they become part of a grand cosmic narrative, stretching from the fiery birth of stars to the silent stillness that might someday characterize the universe's end. They serve as reminders of both the transient beauty of starlight and the enduring nature of matter and energy, which transform but never disappear entirely. White dwarfs embody this constant cycle of transformation. They are the ashes of stars, the bearers of galactic history, and potential seeds of new forms that, while hypothetical, stretch the limits of what we understand about time, space, and energy. White dwarfs also hold particular significance when we consider their potential as time capsules of life's building blocks. During a star's lifetime, nuclear fusion creates heavier elements, which are then dispersed into the cosmos upon the star's death. White dwarfs, therefore, represent repositories of these elements, holding within their cores materials that contribute to the birth of new stars, planets, and potentially life itself. In a galaxy brimming with diverse chemical compositions, white dwarfs add complexity and richness to the interstellar medium, ensuring that each generation of stars is built from increasingly intricate materials. Over countless cycles of star formation and death, these elements combine in myriad ways, eventually creating the conditions necessary for life as we know it. Thus, white dwarfs indirectly contribute to the emergence of life by enriching the cosmos with essential elements. This interconnectedness between stellar evolution and life itself is one of the most profound realizations that astronomy offers us. From the tiniest microbes on Earth to the planets circling other stars, life as we know it owes its existence to the remnants of stars that lived and died billions of years ago. White dwarfs are part of this vast lineage of cosmic ancestors, shaping the environments that, in turn, nurture life's development. Even as they cool and fade, their legacy endures in the elements they have created and dispersed. Reflecting on this legacy, the study of white dwarfs deepens our understanding of the delicate balance required for life. The physical properties of a white dwarf, its mass, temperature, and density, represent the end result of highly complex and finely tuned processes. These stars act as natural laboratories, allowing us to explore conditions that could be replicated in future technologies or even potentially harnessed for long-term energy solutions. Understanding how white dwarfs emit their remaining thermal energy could yield insights into ways of achieving sustainable energy outputs, albeit on a scale vastly beyond current human capabilities. Their stability over billions of years serves as an inspirational model for systems that could, in theory, offer reliable energy for unimaginable durations. Moreover, white dwarfs prompt philosophical questions about mortality, endurance, and transformation. While stars may seem eternal to human observers, they, too, have life cycles dictated by the laws of physics. Their transformation into white dwarfs, and eventual fading into black dwarfs, speaks to a larger theme in the universe, that even the mightiest entities are subject to change, decline, and rebirth. White dwarfs, in this sense, echo themes found in human philosophy, where the cycle of birth, death, and renewal is a central concept. In a universe governed by change, white dwarfs remind us that even in endings, there is continuity. The atoms within our bodies were likely forged in the hearts of stars like the ones that ultimately became white dwarfs. This stellar heritage links all life forms to the stars themselves, embedding a cosmic perspective into our sense of identity and existence. White dwarfs serve as markers of this connection, illustrating how matter is cycled endlessly through the cosmos, passing through stages of creation, evolution, and dissolution, only to be reborn in new forms. In this sense, white dwarfs are far more than mere remnants. They are living archives of the universe's history, preserving the secrets of cosmic evolution, planetary systems, and elemental abundance. Each white dwarf tells a story of the star it once was, the planets it might have nourished, and the galaxy it inhabits. Through the study of these stellar remnants, we gain insights into the forces that shape galaxies, the conditions that allow life to flourish, and the ultimate fate of the cosmos. White dwarfs are silent, steadfast witnesses to the universe's grandest mysteries, illuminating our understanding of space and time, and challenging us to contemplate the vast cycles of creation and destruction that define the cosmos. The exploration of white dwarfs and the fate of low-mass stars is a journey that extends beyond astrophysics. It invites us to ponder our own place in the universe, to appreciate the transient beauty of our world, and to marvel at the interconnectedness of all matter, from the stars to the cells within our bodies. White dwarfs, in their quiet perseverance, embody the mysteries of existence itself, leaving us with a sense of wonder that transcends time, space, and the limits of human understanding. As we delve deeper into the mysteries that white dwarfs embody, we begin to realize that their significance extends to some of the deepest theoretical physics questions about the nature of matter and the fabric of spacetime. These dense, compact objects represent the ultimate struggle between gravitational collapse and quantum principles, a balance that gives rise to the Pauli exclusion principle, which prevents electrons from occupying the same quantum state. This phenomenon is the key to a white dwarf's stability, as it creates the intense electron degeneracy pressure that halts the star's collapse under its own gravity. This remarkable interplay of forces within a white dwarf stands as a testament to the often counterintuitive laws of quantum mechanics. In white dwarfs, gravity is trying to crush the remaining stellar matter into an even more compact state, but electron degeneracy pressure pushes back with equal intensity. This delicate equilibrium produces one of the densest known states of matter outside of neutron stars and black holes. By studying white dwarfs, astrophysicists can test and expand our understanding of quantum mechanics under extreme conditions that cannot be replicated on Earth, probing the very limits of physical law. The mass limit of white dwarfs, known as the Chandrasekhar limit, underscores the precision required in this balance. Discovered by Indian physicist Subrahmanyan Chandrasekhar in the 1930s, this limit describes the maximum mass a white dwarf can possess, approximately 1.4 times the mass of our Sun, before the degeneracy pressure from electrons can no longer counteract gravity. Beyond this threshold, a white dwarf cannot remain stable and will typically undergo further collapse, leading to phenomena like a type I supernova if the mass limit is exceeded through accretion or merger. These supernova events, associated with some white dwarfs, have proven to be of monumental importance in cosmology. Type I supernovae, which occur when a white dwarf in a binary system accumulates enough mass to surpass the Chandrasekhar limit, act as standard candles for measuring cosmic distances. Because they exhibit a uniform brightness, these supernovae allow astronomers to determine distances to galaxies with remarkable precision. This discovery has led to groundbreaking insights, most notably the observation that the universe's expansion is accelerating, a revelation that has propelled the study of dark energy, a mysterious force driving this acceleration. The role of white dwarfs in these discoveries places them at the heart of one of the most profound questions in modern physics: the nature of dark energy. Observing type I supernovae led to the realization that not only is the universe expanding, but the rate of expansion is increasing. This finding implies the existence of an unseen force that counteracts gravity on cosmic scales, influencing the very structure and fate of the universe. Through the lens of white dwarfs and their explosive endpoints, scientists are gradually unraveling the enigmatic force that governs the cosmos on its largest scales. White dwarfs, therefore, serve as unexpected gatekeepers to some of the deepest mysteries of cosmology. By studying their life cycles, scientists have pieced together key information about the geometry of space-time, the composition of the cosmos, and the influence of forces beyond our comprehension. In this sense, white dwarfs occupy a unique place in astronomy, bridging the gap between small-scale quantum phenomena and the vast, seemingly boundless realms of cosmic expansion. They offer a rare point of intersection where the microcosmic and macrocosmic worlds converge, challenging us to view the universe through a holistic lens that unites diverse branches of physics. Adding to their intrigue, white dwarfs possess complex magnetic fields that reveal insights into their internal structures and histories. Some white dwarfs have extraordinarily powerful magnetic fields, up to 1 billion times stronger than Earth's, that influence everything from their surface phenomena to their rotational dynamics. These magnetic fields likely result from the convective motion of electrically charged particles within the white dwarf, similar to the way Earth's magnetic field is generated, though on a much more intense scale. In highly magnetized white dwarfs, these fields can interact with surrounding material in fascinating ways, causing accretion streams to form distinct patterns, shaping the appearance and behavior of these remnants. Magnetic white dwarfs also serve as a laboratory for understanding how magnetic fields influence matter under intense conditions. By observing how their fields alter the star's cooling rates, surface characteristics, and atmospheric composition, scientists gain insights that can be applied to other astrophysical phenomena. Understanding these magnetic dynamics could potentially help explain similar properties in neutron stars, which exhibit even stronger magnetic fields, as well as providing clues about the processes that shape stellar remnants throughout the galaxy. Another captivating area of research in white dwarf astronomy is the study of white dwarf mergers. In some cases, two white dwarfs in a binary system may spiral toward each other, ultimately merging due to gravitational wave emission, a process that loses orbital energy and pulls the stars closer together. Depending on the combined mass of the two white dwarfs, this merger can lead to several outcomes. If the merged mass is below the Chandrasekhar limit, the resulting object may become an unusually massive white dwarf, or potentially transform into a new type of star. If the mass exceeds the limit, the merger can trigger a supernova explosion, providing a spectacular end to the lives of both stars. These white dwarf mergers have gained significant attention, especially in the era of gravitational wave astronomy. When two white dwarfs merge, they emit gravitational waves, ripples in spacetime that carry information about their masses, orbital dynamics, and eventual fates. Observatories like LIGO, Laser Interferometer Gravitational Wave Observatory, are beginning to detect such events, marking a new frontier in our ability to observe stellar evolution through gravitational wave signals. This branch of research is still emerging, but it has the potential to revolutionize our understanding of how white dwarf binaries evolve, merge, and contribute to the broader structure of the universe. Gravitational wave studies of white dwarf mergers could eventually allow us to map binary star populations within the galaxy, providing another layer of insight into stellar evolution and galactic dynamics. White dwarfs, through their mergers and resulting gravitational waves, could help construct a comprehensive picture of star formation, death, and recycling within the galaxy. These observations also serve as another example of how white dwarfs act as cosmic storytellers, each pair revealing a unique history of orbital dance, decay, and ultimately, unity in one final, explosive or transformative event. Even as we uncover these incredible details about white dwarfs, they continue to humble us with mysteries yet unsolved. For instance, the phenomenon of crystallization, where the interior of a cooling white dwarf begins to solidify into a lattice structure, is still not fully understood. Crystallization in white dwarfs was only confirmed in recent years, yet it hints at the complex physics of cooling that these stars undergo in their twilight phases. Crystallization not only influences the cooling rate of a white dwarf but also affects its luminosity and temperature over time, further complicating our models of their evolution. This crystallization process has led to an exciting realization. As white dwarfs cool and crystallize, they release latent heat, slowing their cooling process in a subtle but detectable way. By studying the crystallization rates of different white dwarfs, astronomers gain insight into the fundamental properties of stellar matter and refine the use of white dwarfs as cosmic clocks. This means that crystallized white dwarfs could eventually provide some of the most accurate age estimates for star clusters and, by extension, the galaxy itself. The fact that these stars can crystallize, akin to a vast diamond forming within the cosmos, captures the imagination and adds an almost poetic aspect to the study of white dwarfs. They embody the idea that even as the fires of fusion are extinguished, the legacy of these stars endures in a state of sublime, enduring beauty. White dwarfs, as crystallized celestial diamonds, become symbols of both cosmic permanence and transformation, illustrating that even in silence, the remnants of stellar life continue to impact the universe around them. In the broader context of cosmic evolution, the study of white dwarfs reaffirms that every phase of a star's life, from its fiery birth to its final cooling embers, plays a vital role in the unfolding narrative of the cosmos. Through their existence, white dwarfs reveal the enduring cycles of matter and energy, the intricacies of quantum mechanics, and the profound interconnectedness of celestial phenomena across time and space. They embody the mysteries of the universe, inviting us to question, explore, and dream of realms yet undiscovered. White dwarfs are, in every sense, the quiet watchers of the cosmos, bearing witness to the grand story of creation and, ultimately, of cosmic unity. As we continue to study white dwarfs, one of the most fascinating questions remains their ultimate fate. White dwarfs cool steadily over billions of years, radiating away the last remnants of heat trapped within their cores. However, since the universe is only about 13.8 billion years old, no white dwarf has yet cooled to the point of becoming completely invisible or transitioning into a hypothetical black dwarf, a stellar remnant so cold it emits no light. This means we are observing white dwarfs in an intermediate state, a snapshot in time that reveals their gradual evolution. The idea of a black dwarf is as haunting as it is scientifically intriguing. In a universe much older than our own, perhaps in tens or even hundreds of billions of years, white dwarfs will reach temperatures so low that they emit no discernible radiation, becoming inert and invisible relics of the first generation of stars. At this point, the galaxy would contain vast numbers of these dark, cold, and lifeless remnants drifting through space, a reminder of the cosmos' inevitable thermodynamic cooling, known as heat death, where all energetic processes reach a standstill. The gradual cooling of white dwarfs, therefore, provides us with an existential glimpse into the future of the universe itself. White dwarfs are, in a way, a preview of what awaits all stars that lack the mass to form black holes. Their journey from glowing, vibrant stars to silent, cold objects resonates with the notion that the universe is moving toward a state of maximum entropy, a state where energy is so evenly distributed that no work, no structure, no new formations can arise. White dwarfs become a powerful symbol of this cosmic finality, embodying the concept of a universe where even the most fundamental forces have finally exhausted their transformative potential. This theoretical fate of white dwarfs raises questions about the ultimate structure of matter. If and when white dwarfs do reach the black dwarf stage, they would exist as cold, stable configurations where electron degeneracy pressure continues to counteract gravity. Yet, over unimaginably long time frames, other processes, such as proton decay, a hypothetical event proposed by particle physics theories, might lead these remnants to gradually dissolve, with their matter slowly disintegrating into elementary particles. If proton decay is proven possible, black dwarfs themselves might one day decay, leaving behind only traces of the particles that once formed stars. This decay would represent one of the final acts in the universe's evolution, a point where even the most enduring remnants of stellar evolution cease to exist. Beyond these theoretical explorations, white dwarfs also continue to play a vital role in practical astronomical observations. For instance, white dwarfs are among the most accurate indicators for dating globular clusters, collections of stars bound by gravity, which often contain some of the oldest stars in the galaxy. Since white dwarfs cool at a predictable rate, astronomers can use their temperatures to determine the age of these clusters. The oldest white dwarfs in a cluster correspond to the time at which the most massive stars in that cluster ended their lives, providing a lower limit for the age of the entire cluster. Using white dwarfs as cosmic clocks is particularly significant for understanding the age of the Milky Way galaxy and the early stages of star formation. The presence of ancient white dwarfs suggests that some parts of our galaxy formed within a few billion years after the Big Bang, anchoring our understanding of galactic evolution and helping to create a timeline for the birth of the Milky Way. These stellar remnants essentially function as time capsules, holding clues to the earliest epochs of our galaxy and helping us piece together the puzzle of its formation and evolution. In addition to aging globular clusters, white dwarfs also provide clues about the initial mass function, IMF, of stars in the galaxy. The IMF describes the distribution of stellar masses at the time of a star cluster's birth and has a profound impact on how clusters and galaxies evolve over time. By studying the distribution and properties of white dwarfs, astronomers can infer the original distribution of stellar masses within a population, providing essential insights into how stars of different masses contribute to the overall galactic structure. These insights, in turn, help refine our understanding of star formation rates and the types of stars that populated the early universe. The evolution of low-mass stars into white dwarfs also highlights the role of stellar populations in recycling matter and contributing to galactic chemical evolution. During their lives, stars synthesize heavier elements, a process known as nucleosynthesis, which occurs primarily during the star's final stages. When low-mass stars shed their outer layers as planetary nebulae, they return these elements, such as carbon, nitrogen, and oxygen, back into the interstellar medium. These materials then become part of future generations of stars and planets, facilitating the continuous enrichment of the galactic environment with the building blocks of life. White dwarfs, in essence, are pivotal to this process. They represent a phase in stellar evolution where a star has released much of its enriched material, contributing to the interstellar medium, but retains the core remnant in a stable form. This process is a fundamental driver of cosmic evolution, creating a feedback loop that enables the formation of progressively more complex systems, including planetary systems that may harbor life. In this way, white dwarfs and their predecessors play a crucial role in the broader cycle of matter, enriching the cosmos with the ingredients necessary for diverse astronomical phenomena and possibly even life itself. This enrichment process also provides a deeper understanding of elemental distribution in the universe. The heavier elements produced by stars become increasingly abundant in successive stellar generations, a phenomenon known as galactic chemical evolution. White dwarfs, as remnants of stars that have contributed to this cycle, become markers of how our universe has evolved from a primordial state dominated by hydrogen and helium to one that includes a rich array of elements necessary for complex chemistry. Without this recycling process, the universe would remain forever in a simpler, less dynamic state, lacking the complexity needed for phenomena such as planetary formation, organic molecules, and life. Interestingly, astronomers have found evidence of planetary debris around some white dwarfs, further hinting at the possibility that planetary systems once orbited these stars. In cases where white dwarfs exhibit unusual absorption lines in their spectra, astronomers have determined that these lines often correspond to elements like calcium, magnesium, and iron, elements not expected to be in a white dwarf's atmosphere. This evidence suggests that the white dwarf has captured debris from surrounding planets, asteroids, or comets that once orbited the original star, perhaps long after the star evolved into a white dwarf. These polluted white dwarfs thus serve as a form of cosmic archaeology, offering a window into the fate of planetary systems and the stability of orbits in the aftermath of stellar evolution. Through this lens, white dwarfs provide critical insight into the longevity of planetary systems. The gravitational disturbances that occur when a star loses mass and transitions into a white dwarf can significantly alter the orbits of surrounding planets, often destabilizing them and sending them either into new trajectories or toward the star itself. The presence of planetary debris around white dwarfs, therefore, may indicate that entire systems were disrupted, with material from asteroids or moons ultimately spiraling inward and colliding with the star. This phenomenon raises profound questions about the future of planetary systems, including our own solar system, as it suggests that even stable orbits may be susceptible to major disruptions over long timescales. For our Sun, this scenario means that, billions of years from now, its transformation into a white dwarf could spell the end of the inner solar system. As the Sun evolves, it will first become a red giant, expanding outward and potentially engulfing Mercury, Venus, and even Earth. Eventually, as it sheds its outer layers and leaves behind a white dwarf core, any remaining planetary bodies may experience gravitational shifts that destabilize their orbits. Over eons, these remnants could be pulled into the white dwarf, while distant objects like the Kuiper belt and Oort cloud may drift outward into the galaxy. In summary, white dwarfs represent far more than the quiet remnants of stellar evolution. They embody the cosmic cycle of birth, death, and rebirth, as well as the intersection of physical laws that govern everything from quantum mechanics to galactic structure. By examining white dwarfs, we uncover the history of stars, the processes that build planets, and the forces that drive the evolution of galaxies. These seemingly simple remnants hold answers to questions about the very nature of matter, the structure of the universe, and even the potential for life beyond Earth. White dwarfs are the silent witnesses to the vast tapestry of the cosmos, bridging the ancient past with the distant future. As we further explore the significance of white dwarfs, we must also consider their role in the broader context of cosmic evolution and the formation of galaxies. White dwarfs are not merely byproducts of stellar life cycles, they serve as crucial markers in the timeline of galactic history. Their distribution across the Milky Way provides insights into the processes that have shaped our galaxy over billions of years. The study of white dwarfs in different regions of the galaxy can reveal information about the star formation history of the Milky Way. For instance, a high density of white dwarfs in a particular area might suggest a burst of star formation in that region at a certain time in the past. By mapping these populations, astronomers can reconstruct the history of star formation and identify periods of rapid growth or relative quiescence. This analysis is essential for understanding how galaxies evolve, including their interactions with neighboring galaxies and the influence of dark matter on their structure. Moreover, the spectral analysis of white dwarfs allows astronomers to probe the chemical composition of the galactic environment. The elements found in the atmospheres of white dwarfs can be traced back to the original stars that contributed to their formation. By examining these elements, researchers can gain insights into the processes of nucleosynthesis that occurred during the stars' lifetimes, including the specific conditions under which different elements were created. This information is vital for understanding the chemical evolution of the galaxy, as it highlights how stars recycle matter and contribute to the overall composition of the interstellar medium. The presence of specific heavy elements in white dwarf atmospheres also opens a window into the history of the galaxy's evolution. Elements such as carbon and oxygen, produced in significant quantities by previous generations of stars, become incorporated into the next generation of stars and planetary systems. The study of these elements helps astronomers trace the cycle of matter and identify the role of supernovae and other explosive stellar events in enriching the interstellar medium. This enrichment process plays a crucial role in shaping the chemical diversity of the universe, ultimately influencing the potential for life to emerge in various environments. In addition to their implications for understanding galactic history, white dwarfs also provide valuable insights into fundamental physics. The extreme conditions present in white dwarfs challenge our understanding of matter under high densities. The electron degeneracy pressure that allows these remnants to exist defies classical physics, falling instead under the domain of quantum mechanics. This fascinating aspect of white dwarfs makes them subjects of great interest for theoretical physicists and astrophysicists alike. One particularly intriguing area of research is the study of crystallization in white dwarfs. As these stars cool over time, their interiors can undergo a process similar to that of freezing water turning into ice. The cores of some older white dwarfs are thought to crystallize into solid carbon and oxygen, which could potentially affect their thermal evolution. This crystallization process is still an area of active research, with astronomers striving to understand its implications for the cooling rates of white dwarfs and their subsequent observational signatures. Moreover, some white dwarfs exhibit peculiar pulsations, leading to the classification of specific types such as ZZ Ceti stars. These pulsating white dwarfs change brightness in a periodic manner, allowing astronomers to study their internal structure through a technique known as astroseismology. By analyzing these pulsations, researchers can glean information about the temperature, composition, and evolutionary state of the star, enhancing our understanding of stellar evolution in a tangible way. The relationship between white dwarfs and their progenitor stars is also a critical aspect of this discussion. Understanding how different masses of stars evolve into white dwarfs informs our knowledge of stellar populations and their interactions. The initial mass of a star is the primary determinant of its evolutionary path, dictating not only whether it will become a white dwarf but also the characteristics of that white dwarf. For example, while stars with masses up to about 8 times that of the Sun typically end their lives as white dwarfs, more massive stars follow a different evolutionary route, culminating in supernova explosions and the formation of neutron stars or black holes. The stark contrast between these outcomes emphasizes the importance of mass in stellar evolution and highlights the diverse range of endpoints that stars can achieve. Furthermore, studying white dwarfs helps to illuminate the role of binary systems in stellar evolution. Many white dwarfs are found in binary systems, where they can interact with a companion star. This interaction can lead to interesting phenomena, such as the transfer of mass from the companion star to the white dwarf. In cases where the white dwarf accumulates enough mass to reach a critical threshold, it may undergo a cataclysmic event known as a type Ia supernova. This type of supernova is significant in cosmology, as it serves as a standard candle for measuring cosmic distances and understanding the expansion of the universe. The occurrence of type Ia supernovae is directly linked to the fate of white dwarfs in binary systems, illustrating how these remnants can have far-reaching implications beyond their immediate existence. The study of white dwarfs, therefore, not only sheds light on the life cycles of stars but also plays a crucial role in our understanding of cosmic phenomena that shape the structure of the universe. The cosmic dance of white dwarfs within binary systems provides insight into the interactions that can occur between different types of stellar remnants. For instance, when a white dwarf orbits a more massive companion, the gravitational influence of the companion can strip material from the white dwarf, resulting in a process called accretion. This accreted material can alter the white dwarf's composition and contribute to its eventual fate. These interactions underscore the complex nature of stellar evolution and the interconnectedness of celestial bodies. The life cycle of a white dwarf is not an isolated event. Rather, it occurs within a dynamic environment where other stars, planets, and cosmic materials influence its development. The investigation of these interactions fosters a deeper understanding of how different stellar populations coexist and evolve within galaxies, shaping the larger narrative of cosmic evolution. The study of white dwarfs and their role in the fate of low-mass stars illuminates a complex tapestry of cosmic history and stellar evolution. From their formation to their cooling processes, white dwarfs serve as crucial tools for understanding the life cycle of stars, the evolution of galaxies, and the fundamental physics governing these phenomena. As astronomers continue to observe and study these enigmatic remnants, they unveil new layers of knowledge about the universe's past and future. Through the lens of white dwarfs, we gain a profound appreciation for the intricate web of connections that weave through the cosmos. Each white dwarf is a relic of a star that once burned brightly, and in its cooling, it echoes the themes of transformation and renewal that permeate the universe. The study of white dwarfs not only enhances our understanding of stellar evolution but also resonates with our own place in the cosmos, offering insights into the nature of existence and the transient beauty of the stars. In essence, white dwarfs are not merely endpoints in the stellar life cycle. They represent the culmination of billions of years of stellar evolution and the interconnectedness of cosmic processes. As we reflect on their significance, we are reminded of the remarkable journey that every star undertakes, and the role that these remnants play in shaping the fabric of the universe. The legacy of white dwarfs will continue to guide us as we seek to unravel the mysteries of the cosmos, illuminating the path toward a deeper understanding of our place in the grand narrative of existence. As we delve deeper into the mysteries surrounding white dwarfs, we must also address their role in our understanding of dark matter and the fundamental structure of the universe. The existence of white dwarfs, alongside other stellar remnants, helps astronomers trace the history of matter in the universe, which is critical for piecing together the broader picture of cosmic evolution. The matter that forms white dwarfs primarily consists of the elements produced during the nuclear fusion processes of their progenitor stars. These elements, including carbon and oxygen, represent only a fraction of the matter present in the universe. Much of the universe's mass is thought to be composed of dark matter, an invisible form of matter that does not interact with electromagnetic forces, making it undetectable through conventional means. Despite this, the gravitational influence of dark matter shapes the behavior of visible matter, including stars like white dwarfs. Recent advancements in observational techniques have allowed astronomers to investigate the distribution of white dwarfs across different regions of the galaxy, providing clues about the presence and distribution of dark matter. For example, by studying the motions of white dwarfs in various gravitational fields, researchers can infer the mass of dark matter surrounding them. Such studies contribute to our understanding of galaxy formation and the role that dark matter plays in shaping the structure of the universe. In addition to their implications for dark matter research, white dwarfs serve as important cosmic clocks. Their predictable cooling rates allow astronomers to estimate the age of star clusters and galaxies. By studying the population of white dwarfs and globular clusters, dense collections of stars formed in the early universe, scientists can glean information about the age of the cluster itself. This method is particularly effective because the cooling rates of white dwarfs depend on their mass and composition, which are relatively well understood. When astronomers observe a cluster of white dwarfs with varying cooling ages, they can establish a cooling sequence, which provides a timeline for the cluster's formation. This approach helps to date the oldest star clusters in the Milky Way, offering insights into the early stages of galaxy formation and the subsequent evolution of stellar populations. Moreover, the presence of white dwarfs contributes to our understanding of the potential for habitable planets in the universe. As white dwarfs cool and fade over billions of years, they can create environments that may be conducive to the development of planets. The habitable zone around a white dwarf, where conditions might allow for liquid water, is much closer to the star compared to main-sequence stars. This proximity means that planets could orbit in the habitable zone for a much longer duration than they would around a more massive star, potentially providing a stable environment for life over extended periods. The study of planetary systems around white dwarfs has revealed fascinating discoveries. Some exoplanets have been found to orbit white dwarfs, raising intriguing questions about how these planets survive the violent end stages of their progenitor stars. When a star evolves into a red giant, it expands and engulfs its inner planets. However, evidence suggests that some outer planets can survive this process, either by migrating inward or through complex gravitational interactions. Observing these planetary systems offers a unique opportunity to study the resilience of planets and the conditions that may allow them to thrive even in the aftermath of stellar death. Additionally, the search for remnants of planetary systems around white dwarfs has yielded remarkable results. Astronomers have discovered heavy elements, such as metals, in the atmospheres of some white dwarfs. These elements are thought to originate from the disintegration of rocky bodies, such as asteroids or planetary debris, that enter the white dwarf's gravitational field. By analyzing the chemical composition of these materials, researchers can infer details about the types of planets that may have existed in the system before the star's demise. The discovery of these debris disks around white dwarfs also provides clues about the evolution of planetary systems. It suggests that even after a star has died, the remnants of its planetary system can persist, offering a glimpse into the past and potential future of such systems. This ongoing interaction between white dwarfs and their surrounding materials is a testament to the dynamic nature of the universe and the complexity of stellar and planetary evolution. As we reflect on the significance of white dwarfs, it becomes clear that they are more than just stellar remnants. They are pivotal players in the cosmic drama of evolution. Their existence connects the threads of stellar life cycles, chemical evolution, and the search for habitable worlds. White dwarfs serve as a bridge between the past and future, providing insights into the processes that govern the universe and the potential for life beyond our own solar system. The study of white dwarfs offers profound insights into the life cycle of stars, the chemical evolution of galaxies, and the search for habitable conditions in the universe. These enigmatic remnants serve as markers of cosmic time, illuminating the paths of stellar evolution and the complex interactions that shape the universe. As we continue to explore the mysteries of white dwarfs and their role in the cosmic tapestry, we are reminded of the vastness and intricacy of the universe, where each discovery opens new doors to understanding our place within it. The implications of white dwarfs extend far beyond our immediate observations. They challenge us to think critically about the fundamental principles of astrophysics and the nature of existence itself. By studying these remnants, we not only gain insights into the life cycle of stars but also enhance our comprehension of the broader cosmic environment. Each white dwarf holds a story of stellar evolution, marking the passage of time and the transformations that define the universe's ongoing narrative. Through the lens of white dwarfs, we confront profound questions about the universe's origins, its fate, and our role within it. These remnants of stellar evolution serve as a reminder of the intricate connections between matter, energy, and the forces that govern the cosmos. As we continue to unravel the mysteries of white dwarfs, we embark on a journey that not only enriches our understanding of the universe but also inspires us to seek answers to the most profound questions that define our existence. In essence, the study of white dwarfs encapsulates the essence of cosmic exploration, an unyielding quest for knowledge that transcends the boundaries of our current understanding. As we gaze into the cosmos, we are not merely observing distant stars. We are engaging with the very fabric of the universe, piecing together the fragments of its history and contemplating the potential that lies ahead. As we look to the future, the ongoing exploration of white dwarfs and their implications for cosmic evolution promises to yield exciting discoveries and deeper insights. The pursuit of knowledge in astrophysics is a collective endeavor, and each new finding brings us closer to unraveling the mysteries of the universe. With each observation, we take another step in our quest to understand the fundamental forces that shape the cosmos, enriching our understanding of the intricate relationships between stars, galaxies, and the very fabric of reality itself. The journey into the world of white dwarfs is a testament to the power of curiosity, and the human spirit's unyielding desire to explore the unknown. As we continue to investigate these remarkable stellar remnants, we find ourselves not only uncovering the secrets of the cosmos but also reflecting on our place within it. The story of white dwarfs is a story of transformation, resilience, and the enduring legacy of stars that continue to illuminate the path toward understanding the universe. White dwarfs serve as cosmic reminders of the cycles of creation and destruction that define the universe. As we delve into their complexities and explore their significance, we gain invaluable insights into the intricate processes that govern stellar life cycles, the evolution of galaxies, and the potential for life beyond our planet. The study of white dwarfs is not just an exploration of stellar remnants, it is an exploration of our cosmic heritage and our quest for knowledge that transcends time and space. Through the lens of white dwarfs, we embrace the interconnectedness of all things in the universe and acknowledge the profound mysteries that remain. As we continue our journey through the cosmos, let us carry forward the spirit of inquiry that drives us to seek answers and deepen our understanding of the remarkable universe we inhabit. In the grand narrative of cosmic evolution, white dwarfs are but one chapter, yet their significance resonates throughout the fabric of space and time, inspiring generations of astronomers and dreamers to reach for the stars and unlock the secrets of the universe. As we continue to explore the realm of white dwarfs and their significance in the cosmos, it's essential to delve into their potential end states and the ongoing research surrounding them. While white dwarfs represent the final evolutionary stage of low-mass stars, they can take on a variety of forms depending on their mass, composition, and the presence of any companions. Understanding these distinctions is crucial for our broader understanding of stellar evolution. After a white dwarf forms, it will continue to cool and fade over billions of years, transitioning into a state where it emits little to no light. In this cooling process, the surface temperature of a white dwarf drops, leading to a gradual dimming known as the white dwarf cooling track. This cooling track provides astronomers with valuable data, as it allows them to establish the age of star clusters by comparing the temperatures of the white dwarfs within them. This aspect of white dwarf research is pivotal for constructing a timeline of stellar evolution and gaining insights into the age of the universe itself. Interestingly, some white dwarfs are not isolated entities. They may belong to binary systems where they can interact with companion stars. In such cases, the dynamics between the two stars can lead to phenomena such as accretion, where material from the companion star is drawn onto the white dwarf. This process can reignite nuclear fusion in the white dwarf, resulting in a nova, a cataclysmic explosion that can temporarily outshine entire galaxies. These novae events provide astronomers with an opportunity to study the behavior of matter under extreme conditions and contribute to our understanding of stellar processes. However, not all binary interactions result in novae. If the white dwarf accretes enough mass from its companion, it can approach the Chandrasekhar limit, approximately 1.4 times the mass of the Sun. Once this limit is exceeded, the white dwarf can no longer support itself against gravitational collapse. This leads to a Type I supernova, a powerful explosion that occurs when a white dwarf undergoes runaway nuclear fusion. Type I supernovae are of particular interest to astronomers because they serve as standard candles for measuring cosmic distances, providing critical data for understanding the expansion of the universe. The role of white dwarfs in Type I supernovae also has profound implications for cosmology. The consistent brightness of these supernovae allows astronomers to determine the distance to their host galaxies with great accuracy. This capability has played a crucial role in revealing the accelerating expansion of the universe and the existence of dark energy, an enigmatic force that drives this acceleration. The connection between white dwarfs and Type I supernovae thus links stellar evolution to fundamental cosmological questions, illustrating the interconnectedness of various astronomical phenomena. The research surrounding white dwarfs is continually evolving, fueled by advancements in observational techniques and theoretical models. For instance, upcoming space telescopes, such as the James Webb Space Telescope, are expected to provide unprecedented views of white dwarfs and their environments. These observations will deepen our understanding of their cooling processes, chemical compositions, and the role they play in the galactic ecosystem. One intriguing area of research focuses on the chemical makeup of white dwarfs, particularly in relation to the heavy elements found in their atmospheres. By studying the spectral lines emitted by white dwarfs, astronomers can identify the presence of various elements, such as calcium, magnesium, and iron. The detection of these elements offers insights into the history of accretion events and the potential for planetary debris to affect the white dwarf's composition. Moreover, the discovery of unusual chemical signatures in some white dwarfs has prompted questions about their formation processes. Some white dwarfs exhibit signs of having accreted material from peculiar sources, such as interstellar clouds or even other white dwarfs. These observations challenge conventional models of stellar evolution and underscore the need for a more nuanced understanding of the processes that govern white dwarf formation and evolution. The mysteries surrounding white dwarfs extend beyond their physical characteristics. They also provoke philosophical questions about the nature of the universe and our place within it. The study of these stellar remnants encourages us to ponder the cycle of life and death among stars and the intricate processes that lead to the formation of planets, and potentially life. As we gaze at the night sky, the light from distant white dwarfs serves as a reminder of the cosmic history that has unfolded over billions of years, shaping the universe we inhabit. The exploration of white dwarfs also highlights the importance of interdisciplinary collaboration in advancing our understanding of the cosmos. Astrophysicists, cosmologists, and planetary scientists must work together to synthesize findings from various fields and construct a coherent picture of stellar evolution. By bridging these disciplines, we can unlock new insights into the life cycles of stars, the formation of planetary systems, and the evolution of galaxies. As we look ahead, the quest to unravel the mysteries of white dwarfs promises to yield exciting discoveries and deepen our understanding of the universe. With each new observation and theoretical advancement, we inch closer to comprehending the complex interplay of forces that govern stellar life cycles and the cosmic evolution of matter. In summary, white dwarfs are not merely the remnants of low-mass stars. They are integral components of the cosmic landscape that inform our understanding of stellar evolution, dark matter, and the fundamental nature of the universe. Through their cooling processes, interactions with companion stars, and the insights they provide into the age of the galaxy, white dwarfs illuminate the intricate connections that bind the cosmos together. As we continue to investigate these enigmatic objects, we not only gain insights into the life cycle of stars but also engage with the broader questions that define our existence. The study of white dwarfs encapsulates the essence of astrophysics, a relentless pursuit of knowledge that transcends the boundaries of time and space. With each new discovery, we deepen our appreciation for the wonders of the universe and the remarkable stories that unfold in the vastness of space. White dwarfs serve as powerful symbols of the cycles of creation and destruction that define the universe. As we continue to explore their complexities and implications, we open new avenues for understanding the intricate processes that govern stellar evolution and the potential for life beyond our planet. The ongoing investigation of white dwarfs is not just a quest for knowledge, it is an exploration of our cosmic heritage and our place within the grand narrative of the universe. The story of white dwarfs is one of resilience and transformation, a testament to the enduring legacy of stars that continue to illuminate the path toward understanding the universe. As we move forward in our exploration of the cosmos, let us remain committed to the pursuit of knowledge and the unraveling of the profound mysteries that define our existence. In this pursuit, we embrace the spirit of inquiry that drives us to seek answers and deepen our understanding of the remarkable universe we inhabit. The legacy of white dwarfs and their role in the cosmic tapestry serves as a reminder of the interconnectedness of all things in the universe, urging us to reflect on the mysteries that remain and the discoveries yet to be made. As we gaze into the cosmos and contemplate the nature of white dwarfs, we are inspired to continue our journey of exploration and discovery, driven by a desire to unlock the secrets of the universe and our place within it. The study of white dwarfs is not merely an academic pursuit. It is a celebration of the human spirit's unyielding quest for knowledge and understanding, a journey that transcends the boundaries of time and space, illuminating the path toward the unknown. In this grand endeavor, we honor the legacy of those who have come before us, paving the way for future generations of astronomers and scientists to continue the exploration of the cosmos. The story of white dwarfs is but one chapter in the rich narrative of cosmic evolution, and as we unravel its mysteries, we embrace the limitless potential of discovery that lies ahead. The journey through the cosmos continues to reveal the intricacies and marvels of celestial phenomena. As we deepen our understanding of white dwarfs and their pivotal role in the life cycle of stars, we find ourselves navigating through a landscape rich with implications for both astrophysics and our own existence. One of the most compelling aspects of white dwarfs lies in their ability to serve as cosmic chronometers, tools for measuring the age of various stellar populations and understanding the evolutionary history of our galaxy. To comprehend this, we must delve into the physics of white dwarfs. When a low-mass star exhausts its nuclear fuel, it undergoes a series of complex processes leading to its transformation into a white dwarf. During this phase, the star sheds its outer layers, expelling them into space and creating a stunning planetary nebula. What remains is the hot, dense core composed primarily of carbon and oxygen. This remnant is incredibly stable, no longer undergoing nuclear fusion, and gradually cools over billions of years. The cooling rate of a white dwarf is a crucial factor in determining the age of star clusters. As white dwarfs emit light primarily through thermal radiation, they initially shine brightly but steadily cool over time. The relationship between temperature and luminosity follows a predictable track, allowing astronomers to estimate the ages of the white dwarfs by their current states. By studying groups of white dwarfs within globular clusters, dense groups of stars formed around the same time, astronomers can create a timeline for stellar evolution, shedding light on the history of star formation in our galaxy. These measurements have profound implications for understanding the age of the Milky Way itself. By examining the oldest white dwarfs, scientists can ascertain the minimum age of the star cluster they inhabit, thereby providing a lower limit for the age of the galaxy. This knowledge helps us piece together the timeline of cosmic events, including the formation of the Milky Way and the various stages of star formation that have occurred since its inception. Furthermore, The presence of white dwarfs contributes to our understanding of the chemical evolution of galaxies. As they cool, white dwarfs reveal their elemental compositions, which can offer clues about the material from which they formed. The process of nucleosynthesis, whereby elements are created within stars during their life cycles, contributes to the enrichment of the interstellar medium, the gas and dust that make up the galaxy. When stars explode as supernovae, they disperse heavy elements into space, which may later be incorporated into new stars and planetary systems. This cycle of birth, death, and rebirth among stars highlights the interconnectedness of cosmic processes and the ongoing evolution of the universe. The cooling white dwarfs also play a vital role in probing dark matter, a mysterious substance that makes up approximately 27% of the universe's mass-energy content. The gravitational influence of dark matter affects the motion of stars and galaxies, yet its nature remains elusive. Some researchers are investigating the potential for using white dwarfs as probes of dark matter. By studying the distribution of white dwarfs in different regions of the galaxy, astronomers hope to gain insights into the distribution and density of dark matter, ultimately unraveling one of the greatest mysteries of modern astrophysics. As we consider the fate of low-mass stars and their eventual transition into white dwarfs, we must also acknowledge the influence of stellar interactions within binary systems. Binary stars, two stars bound together by gravity, can dramatically alter the life paths of their individual components. When one star in a binary system becomes a red giant, it may overflow its Roche lobe, transferring mass to its companion. This mass transfer can rejuvenate the companion star, leading it to evolve faster than it would have on its own. Such interactions complicate the expected cooling tracks of white dwarfs, as their evolution is no longer solely determined by their initial mass. Additionally, some white dwarfs exhibit peculiar behaviors that defy straightforward explanations. For instance, there are a subset of white dwarfs known as magnetic white dwarfs, which possess strong magnetic fields. These magnetic fields can influence their cooling rates and spectral characteristics, leading to unique observational signatures. Understanding the origins of these magnetic fields and their impact on stellar evolution remains an active area of research, highlighting the complexity and variety of white dwarf characteristics. In recent years, advancements in observational technology have opened new frontiers in the study of white dwarfs. The advent of space telescopes equipped with high-precision instruments allows astronomers to obtain detailed spectra of these stellar remnants. Such observations enable the measurement of their chemical compositions, surface temperatures, and magnetic fields with unprecedented accuracy. As we gather more data on white dwarfs, we can refine our models of stellar evolution and the underlying physical processes that govern their formation and behavior. The future of white dwarf research holds exciting possibilities. Projects such as the European Space Agency's Gaia mission are poised to revolutionize our understanding of the Milky Way and its stellar populations. By mapping the positions, distances, and motions of billions of stars, Gaia provides a wealth of data that will enhance our knowledge of white dwarfs and their contributions to the galaxy's dynamics. This mission is expected to reveal new insights into the distribution of white dwarfs and their interactions within stellar clusters. As we reflect on the significance of white dwarfs, it is clear that these stellar remnants offer more than just a glimpse into the fate of low-mass stars. They serve as cosmic markers, illuminating the history of the galaxy and providing crucial data for our understanding of stellar evolution. White dwarfs remind us of the cycles of creation and destruction that shape the universe, echoing the profound interconnectedness of all cosmic entities. In summary, the study of white dwarfs unveils a tapestry of cosmic evolution that spans billions of years. Their life cycles, interactions, and cooling processes reveal critical information about the age of the galaxy, the formation of elements, and the mysteries of dark matter. The ongoing exploration of these enigmatic objects not only deepens our understanding of stellar evolution, but also enriches our appreciation for the intricate workings of the universe. As we continue our journey through the cosmos, let us embrace the mysteries that white dwarfs embody and remain steadfast in our quest for knowledge. The story of these stellar remnants is a testament to the resilience of stars and the enduring curiosity of humanity, a reflection of our unyielding desire to comprehend the universe we inhabit. The legacy of white dwarfs invites us to ponder our place in the cosmic narrative, inspiring future generations of astronomers and scientists to embark on their own journeys of discovery. With each new finding, we not only illuminate the paths of white dwarfs but also shed light on the broader questions that define our existence, questions about life, death, and the intricate processes that govern the cosmos. As we gaze into the vast expanse of space and contemplate the fate of low-mass stars, let us remain committed to the pursuit of knowledge and the unraveling of the profound mysteries that lie ahead. The exploration of white dwarfs and their role in the universe serves as a reminder of the beauty and complexity of the cosmos, a call to action for those who seek to understand the stories written in the stars. In this grand endeavor, we honor the legacies of past astronomers while paving the way for future explorations. The study of white dwarfs encapsulates the essence of astrophysics, a relentless pursuit of knowledge that transcends time and space. As we navigate this journey, let us remain open to the wonders that await us, ever eager to unlock the secrets of the universe and our place within it. In conclusion, the story of white dwarfs is one of transformation, resilience, and interconnectedness. These stellar remnants illuminate the intricate processes that govern the universe, reminding us of the cycles of life and death that shape our understanding of existence. As we delve deeper into the mysteries of white dwarfs, we not only enrich our knowledge of stellar evolution but also engage with the profound questions that define our cosmic journey. The exploration of these celestial phenomena is not merely an academic pursuit, it is a celebration of the human spirit's quest for understanding, a journey that invites us to explore the mysteries of the universe and our place within it. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.